My name is Hedley Appley, and in this session we'll take a PTCs model-based systems engineering solution. I'll start out by looking at some of the challenges of systems engineering, and then look at PTC's MBSE solution in more detail, including model-based systems engineering, asset-based modular design, and system product lines. We'll then look at how we integrate systems engineering into your life cycle and with your existing tool chain, look at the systems engineering process and its governance, and finish off with some examples of model-based systems engineering in action. So let's start by taking a look at general systems engineering challenges. We're all seeing a broad impact of physical and digital convergence. Smarter products, connected products, even smart cities, smart farms, and smart manufacturing. One example is the automotive industry, where cars used to be purely electrical and mechanical, and then were extended with software, with new user interfaces, sensors, electronic controls becoming smart products. And now the connectivity of those smart cars, so they can communicate not only with GPS and control centers, but also with each other for autonomy. This is really an evolution into products being part of a larger system, and this means that we need multidisciplinary product development to cover all those different domains. So let's take a deeper look at some of the challenges of systems engineering for smart connected products and systems. Firstly, we're seeing a significant growth in the complexity and functionality of the systems and their software. In fact, a much larger share of the product cost is now software. We're also seeing systems being built of subsystems, so in a modular way, plugging subsystems together to build larger systems, either provided by one organization or by partners, or even by disconnected organizations. Certification and regulation are also becoming more important, particularly in industries such as aerospace, automotive, rail, energy, etc. The second main thing that we're seeing is larger and more distributed multidisciplined teams with barriers to communication and collaboration. So they need a common place to work together and share their goals and get stakeholder buy-in. And as well as those focused systems engineering challenges, we're always seeing the same challenges of delivery on time, to quality, and reducing cost. And particularly with systems engineering, we need to see in most cases requirements traceability and impact analysis, so that we can make the decisions about where the functionality should be best located. And then in systems engineering specifically, we're seeing some new trends. So we're seeing more rapidly changing requirements and shorter iterations of delivery. We're seeing models as the core of communication between all stakeholders, incremental functional analysis, executable requirements with SysML, architecture to enable parallel teams to work on separate subsystems, and also the need for asset-based modular design of subsystems and their interfaces and system variability. As you can see in this chart, people are moving from having no standards to being standards compliant, activity-based to goal-based, no integrated engineering to systems engineering, as well as waterfall or V-model processes applying some agile and incremental approaches, moving from small co-located teams to large globally distributed teams, and particularly moving from document-based using Excel, Word, textual requirements to model-based systems engineering. And model-based systems engineering is now recognized as the most agile approach to systems engineering. And the time is now. These recent papers from PTC on how smart connected products are transforming competition and companies, from Michael Porter and our CEO Jim Heppelman, pull out some important points. So smart connected products require functional rethinking of the design, and at the most basic level, product development shifts from largely mechanical engineering to true interdisciplinary systems engineering. This means you need a focus on systems and not just discrete products. It also means you need to consider systems of systems. As products become components of broader systems, the opportunities for design optimization multiply. So now that we've taken a look at the challenges in systems engineering, let's take a look at PTC's model-based systems engineering solution. PTC provides a collaborative, model-based systems engineering solution, a holistic, multidisciplinary and collaborative approach to designing and maintaining complex systems. PTC's model-based systems engineering solution fits across the top of other engineering disciplines so that you can decide the best place to implement particular functions using simulation and trade study analysis. Then, once you've designed your system, you can allocate those functions to software, electrical, mechanical, hydraulic and other types of engineering implementation. Requirements engineering also fit within the scope of model-based systems engineering, either internally or linked, and also we need to consider the process for systems engineering. So let's take a look at our approach to model-based systems engineering. The first concept is that of unify, bringing together all the domain engineers so they can work using a common language and a shared environment with access to the same information. This helps them find problems, discuss and make decisions, and get stakeholder buy-in. We achieve this by using a live underlying database in Integrity Modeler, the modeling tool. Multiple users can share the same databases and the same information on all of their models. So let's take a look at an example model. In the model, we have both diagrams and data that's used on those diagrams. And the data is stored in a dictionary and can be used on more than one diagram. So diagrams are just views of the underlying data. They're not pictures like PowerPoint or Visio. This is a real model with views onto the underlying database. So here I've created a diagram with two simple blocks on it and named them block 1 and block 2. I can create another diagram, so here's diagram 2, and use those same model items on this new diagram. I can put them in different places, link them in different ways, and create a view for a different audience. If I make changes, so if I rename one of these items, so let's change the name of this item, you'll see that it changes both in the database, in the dictionary, so here we have the new name item, and if we go back to the first diagram we can see that the names change there. So we have consistency throughout the whole model, no matter how many users are updating it at the same time. As well as the concept of the underlying database, we used to use a common language, the standard SysML, for systems modeling. Here are some examples of a context diagram, a requirements diagram, which can be linked and synchronized with external tools or used directly for modeling requirements in our systems model. We can elaborate them and have hierarchies and networks of requirements. We can also model our use cases, our functions, our structure with our blocks, and then link and trace between them. And the model has all of those links and traces built in for all of the traceability and impact analysis you need to ensure you build the right system and build the system right. Once we have that model, we can then look at it and simulate it, run trade study analysis to ensure we have the right functional design, to ensure we have stakeholder buy-in, and we can record the results and keep those as records, and we can also simulate with third-party tools such as MATLAB Simulink. So let's take a look at functional simulation with Integrity Modeler. So here's our basic underlying model. This is a truck called a street scooter that we want to simulate driving around streets to see how its electric power system functions. It has a detailed design of the structure, the functions and the requirements, and how all the parts fit together to quite a detailed level of design. We can also model the simulation, and this is a co-simulation of parts talking to each other, and this is then used by Integrity Modeler's SciSim to simulate the functional design. So let's run up SciSim, and here we have a mock-up interface showing the dissipated energy, remaining energy and speed of our truck. And when we run the simulation, it uses the algorithms inside the model to work out how much power is used as we accelerate, slow down, turn around the curves and speed up again. We can see the energy dissipating from the battery, and in the graph at the bottom we can see acceleration and deceleration and that power use. So we can use this with the stakeholder, with other engineers to review the functional areas of our design to check that we have our design right. If we find problems here, they're much cheaper to fix than later, even when we've started to build prototypes or physical systems. As well as simulation and that modeling for communication, we also need to make sure we safeguard our design and that we're implementing in a traceable way. We need to do that by designing in quality rather than testing it in after we've finished. So as well as making sure that people apply the modeling language standard in a compliant way and correctly, we also need to provide traceability and automated tools for early problem identification. So let's take a look at traceability first. In this example, we're starting with a block, a part of a system, and we want to trace back up before we make any changes to see what requirements this block is implementing, to see the impact before we make the change. So we can jump from the block to find out, in this case, the functions that the block implements, and then trace those back up to the use case that those are implementing. So here we have the load and the unload functions, which are then used by the use case operate truck. And by using our relationships view, we can then navigate and find all of the requirements that this use case and therefore these functions and this block implements, giving us full end-to-end traceability in the model, all the way from requirements through functional design to system structure. We also want to check that the design is a good design, and we provide Integrity Modeler Reviewer for that purpose, and here we can run automated reviews, and we have 110. You can add your own and configure the reviews we provide to provide firstly a management dashboard about the completeness and correctness of our model. Here we can see we're in pretty good shape, but we still have some work to do. And then further down we can see all of the problems and the number of those problems, and even see them ranked by the percentage. And in this case we can see that we have unscoped use cases. If we don't understand what that problem is, we can find more information about the problem, the consequences of not fixing it, and the strategy for fixing it. So very rapid and automated review of our design, helping us again find problems much earlier in the life cycle when they're much cheaper to fix. We also have good agility in our models. So we have approaches for agile modeling, doing just enough modeling to deliver the system design and deliver the product. We can also model in an iterative and additive evolutionary way. One of the great features to help us with this agile modeling is that we have the idea of increments in our database, so in the dictionary. And incremental delivery allows us then to build up our system over time, delivering functional parts in an incremental way. So we can define increments, and then in this case we can allocate particular use cases which have groups of functions and groups of system structure to those use cases. So here we're allocating the drive use case to this increment. And as we look at each of the use cases, we can see all of the increments that they are allocated to. So we have really agile modeling using incremental delivery of the functions of our system design. So now let's take a look at asset-based modular design. So as the systems we build become even more complex and large, we have the challenge of building systems of systems. SysML is great for designing systems, but as this complexity grows, the models can become very large and complicated. We need to understand how the subsystems plug together, how their interfaces are defined almost as contracts between systems, how to work with distributed teams working on different areas of the product. To solve this problem, we provide an asset-based modular design approach, using an asset library to link up models, with the models representing either subsystems or systems built of other systems, so systems of systems. In this diagram, we're showing one simple layer of depth. Of course, that could be chained to any depth. The asset library implements another standard, we implement the OMG's reusable asset specification for the meta model of the asset library, and the links to modeler, to SysML and the UML, are implemented using another standard, the OSLC asset specification. So again, this is all standards based, but a great way of breaking up a problem into small chunks and linking them all together. So let's take a look at this in action. So firstly, we'll start off with a model in Integrity Modeler of a drive axle, so part of an overall truck. This has a fairly complex internal design. It could have electronics, hydraulics, mechanical parts, and it has a number of interfaces. In this case, a flange, a clamp to the spring, and other interfaces. All we need to do to make this an available subsystem is firstly set it as an asset, and then just drag and drop it into a separate Integrity Asset Library. So this is outside the model database in a more widely available asset library that can be accessed across the globe by other engineers who want to reuse our drive axle system design. Now that it's published, we can see that drive axle in asset library. So here's the view into the reusable asset specification meta model. You can see the interfaces, lots of descriptive information to help us find it and reuse or use for the first time. So now we're in our higher level system of system design. We can reuse that asset. So just drag it straight onto a diagram, choose the modeling language we're using, in this case SysML, and now we have the drive axle with its version, so full configuration management. And we can use the internal design, so the block and the interfaces of that drive axle without all the complex real internals and detailed parts of our subsystem. So it's treated very much as a black box with interfaces that we can then use to plug together our system of systems. This is a unique approach from PTC to designing systems of systems using asset-based modular design. Once we've used those assets, we can then also navigate across the links. So we can jump from the model to find that asset in the asset library to read more information about it, and we can also jump to the model that implements and designs that detailed asset. So this gives you real power for modularity at design time, helping you design the same way that you build. So now let's take a look at system product line engineering. The third main challenge area is that of system families. So we expect to see product families later in the product lifecycle, but early on we also need to consider families during systems engineering. Organizations are seeing explosions in their system families. They have to decide between the various options. They have to customize existing capabilities to suit new client requirements. They want to redeploy common systems and software to the market, and really improve the time from requirements to cache. In our solution, we allow you to extend the model, the model-based systems engineering model, to represent a family of systems, or as we say, a 150% model or an overloaded model. And we can see that on the top right with two types of engine in our truck. And then in parallel, we can design the variability of our system using orthogonal variability modeling. We'll take a look at that in a moment. And then using the combination of our systems model and our variability model, we can make choices and decide on the various features, the various variants, using a variant selector. Once we made those choices, we can automatically generate product instance models that we can then simulate and run trade study analysis on to decide if they are good possibilities for system and product design. If not, we can throw them away, come back and maybe change either the underlying system model, the variability model, or make even different decisions and regenerate another product model and test it again to see if it's a good design. The variability model is in concept very simple. Just two types of thing, a variation point, which is a triangle, and a variant with a V in the corner. In this example, we have a truck which can be a city truck or a long haul truck, and based on the choice you can only choose one, either a city truck or long haul. You get either a different type of cab, day cab or sleeper cab, a different length of chassis, or a different number of axles. So let's take a look at this in action. So back into Integrity Modeler to look at model-based product line engineering. Let's start out by looking at our overloaded or 150% model. Here we can see that there are two types of cab. Clearly, a truck can't have two cabs at the same time. But as well as that family model, we also have the variation model. So here's the variation point for accommodation with city truck, overnighter. And based on those choices, it will select two different types of cab. So once we've created that design, we can then go and make decisions about which of those variants we want to include. So here we can choose the city truck, and by including that, that will automatically exclude the overnighter. We can use this decision set editor in Integrity Modeler, or the variant selector, which is probably more appropriate for marketing people or customers to show them the same types of decision. And here we can maybe change or override that decision and change it from a city truck to an overnighter. Once we made those decisions, we can then use Integrity Modeler to automatically create a product instance model. So now we're using those decisions that we made earlier to build a new model traced and linked back to the original based on that family model, variability model, and the decision set. And if we open the same diagram, we can now see that the truck has only one type of cab, the sleeper cab for long haul. We can now run trade study analysis, simulation, and bear in mind this is a very simple example. So great productivity, great reuse, and consideration of variation. Really powerful tool for systems engineers. Now let's take a look at lifecycle integration. As we saw earlier in the session, model-based systems engineering really becomes the platform which is shared between all stakeholders and all the different domain engineers, really enabling systems thinking. That means it needs to be connected to the other tools in the toolchain, connected to requirements if you use a requirements engineering tool, connected to simulation and co-simulation with third-party simulation tools, connected down the life cycle into ALM and PLM, and maybe even connected to create outputs such as documentation or flow down into software design and code generation. We provide many of these integrations to connect model-based systems engineering in your toolchain. So firstly, let's take a look at an example around automated code generation. At PTC, we have a technology called ThingWorks for implementing the Internet of Things. It's a multi-tier architecture running right from the devices, so software, smart connected devices. For example, in this example we have a charging system and a car with software running on those devices. not only to control them and control their interactions and the interactions with users and other systems, but also to feed data back up to the cloud through data links and maybe up to control center applications and dashboards. ThingWorx enables this implementation of this architecture. But in Integrity Modeler, and particularly with MBSE, we can design that architecture. So we can design how the user will interact with our overall system and system of systems. We can design the components, the subsystems and their interfaces and how they should be connected and what data should flow between them. And we can also design the detailed code that runs on those edge devices. Integrity Modeler has always been used for this multi-architecture design of systems and software, and already generates code to things like C++ and Java and other languages. More recently, we've added integration to automatically generate for PTCs ThingWorx. So let's take a look at that in action. So here we have an Integrity Modeler model. This is a car charging station and car charging system which has requirements for the driver and managing the system. And those are then satisfied or refined by use cases. So using the charging station, charging a car, and also detecting fraud, so malicious attacks on our charging stations. Each of those use cases then has internal design of the detailed requirements, the functions such as charging and payment, and the subsystems involved, so the parts of our system, like the car and the charger. And that model is then implemented in real life. So here we have the real charger, the real car, and a connection to the internet, and maybe a control center with a dashboard. As well as the system, we can also model the software within Integrity Modeler. And here's an example of the charger system and its software design, using models and diagrams to define all the details about the structure of the software, its functionality, its parameters and its logic, and the various states that it can go through. As well as the charging station, we're also modeling the software that runs on the car. And by setting a simple flag on these items, we can say that they are specifically for one language. It could be Java, it could be C++, it could even be ready for ThingWorx. So this is a generic design that can be generated into many different outputs. In this case, we're generating ThingWorx ready code for our Internet of Things stack. Here's an example of the code that's been generated for the car. You can see it's preloaded with all the ThingWorx items necessary to feed the data up to the cloud and up to a mashup, and also to be controlled remotely by the applications. We also have the software for the charger, and as well as all the code you need to communicate up to the cloud and send information and receive instructions, we also have code to communicate between devices for systems that don't necessarily need to connect to the internet while they're running, but want to connect to each other, like the car and the charging station. Once we've modeled and designed that code, checked it, reviewed it, we can then generate the code and deploy it onto the charging station and onto the car. We can simulate it before we do the physical deployment, and it's shown here with a simulation of the user interface. So here's the user interface of the charging station. It's saying connect the car. So in our simulation or in the real life with the software, we can connect the car. As we saw in the state diagramming and the state models, that will then check that this is a real car rather than a fraud attempt. The car will then tell the charging station what charge it already has in the batteries. Once that's confirmed, then the user interface will ask the user, the driver, how much charge they want to add to the car. In this situation, this is actually Integrity Modeler's SciSim simulating the user interface based on the logic in our model. So here we're interacting with the simulation, telling the simulation and the car charger how much we want to charge, and then we're starting the charge with the go button. You can see there's information about the current charge and how much is being added. And then the simulation will run, and if we've deployed live software, the live software will run and start charging the car. As this is a ThingWorx deployment, that information about the charging is also being streamed to the cloud, and here we have a ThingWorx mashup actually monitoring that data that's coming up from the Boston One charger. We can see the battery level, the charge to add, and we can see the charge as it's being added to the car. We could also do other things here, like turn on the power, turn off the power to the charging station and control it remotely. So as well as generating the code that runs on the devices, we also generated the code that sent the information up through to ThingWorx, through the cloud, to the mashup and the dashboard. However, as we mentioned earlier, the code can also communicate between devices. So if there's no internet in the loop, we can elegantly disconnect the car from the charging station without overcharging, for example. And then when the charging is complete, we can tell the user to disconnect the car and we're finished. So that's a very simple example of modeling software and integrity modeler based on a higher level system design, automatically generating code that can be simulated before we deploy, and then actually deployed and used in real life. So that's one example of connection. We also mentioned simulation, so we can simulate our designs before we even generate the code. And that helps us find problems, share the designs, the functionality with all the stakeholders. Maybe they don't understand detailed modeling and diagramming, but before we create any physical prototypes or software prototypes, we can share the logic and share the understanding of the system, review it and improve it with simulation. So let's take a look at Integrity Modeler SciSim. So again, it's based on an underlying model, an underlying system design, and also a design for the simulation, so what parts are connected together and what displays we want to provide on the simulator. Using that, then we can run SciSim, and also running, in this case, we can run it with ThingWorx mashup in the loop. So SciSim here you can see running in the background, but in the foreground we have a ThingWorx mashup which is receiving data directly from the model. We can also take real data from real devices and feed that into the simulation in SciSim and run it again, comparing our model-based simulation with our model-based algorithms and the actual data received from a real car driving around the streets. In this example we can see that there's a difference, and this, after investigation, was found to be due to skidding as we were accelerating and the lack of a traction control system limiting the torque. So we'll add one of those to the model and set the torque limit to lower than previous, and that will automatically regenerate the code with a different torque limit set. So here's the code that we've regenerated automatically in the background, which we can then deploy to the car and run the test again. You'll now notice that we're running the simulation. We've got the torque limit set to 250, and in the background you'll see that the line for the simulation power use and remaining charge in the battery now matches the simulation. So we've improved our simulation model, and we've also improved the system and the end product based on simulating our systems models. So we're simulating with the model in the loop. We can also simulate now with the IoT mashup in the loop, so the Internet of Things and the real device data in the loop. The next area, connectivity, and we mentioned linking to requirement systems, things like Integrity Lifecycle Manager, great requirements integration there, and maybe other tools like Doors. We have integration with things like MATLAB Simulink, but there's also great benefit to be had from integrating with PLM systems such as our own Windchill and PDM Link. So there's various levels of integration. Firstly, with Integrity Modeler and Integrity Lifecycle Manager, bidirectional requirement synchronization and trace and link management. This is a first step in getting towards a whole linked toolchain and traceability across the whole toolchain, from requirements through to functional models in our system model, structural model, maybe even tracing and linking to variability model if you're modeling system product lines, and then through into your parts in your bill of material and maybe even your options and variants. The way we do that, and here's one example, is with two concepts. Firstly, improving productivity, and then we'll come back later and look at traceability. So let's look at a productivity example in action. So here we have a model in Integrity Modeler. This is a systems model with blocks and their parts representing our system structure. We can also see the information that's on this diagram in the dictionary. This is a real model, not just a picture, and all the data exists in the model database. So here we have the wheels, the engine, the transmission. And as well as that structural information about our product, and in this case it's a product family because we have more than one engine type and more than one transition type, we also have the orthogonal, the parallel variability model. And in this example we can see the variability of the transmission. So we have automatic or stick shift, and based on the choices of those variants we have different inclusion of different parts. Now, of course, all this information is really useful later on in the life cycle. We can flow down into our PLM system. So we can start a wizard to export the information. Here we're starting with the parts, the blocks, and also it will automatically show us the variability that's linked to those items. We can decide where to output that file, and if we're a power user we can maybe change the configuration, but typically that's all fine and nothing you need to get involved with. Once we're happy with the location for export, we can then start the export, and it'll create a log for us, so we have a full audit trail of everything that's being created in the file to be loaded into Windchill as a starting point for product design and product engineering based on a high-level system. So here we are now in Windchill with an empty folder, and we can import those system blocks as first cut bill of material configurable parts. So here are parts representing all of those items from the system model. This saves us retyping, making errors, communication. It also ensures that this first cut structure matches exactly the structure we designed at the system level. Of course, we could then go and elaborate and add all the detailed parts that wouldn't be modeled for systems. We can also then assign option sets so that we can make use of the variability that we define in the system model here at the bill of materials parts level. So if we take a quick look at the filter, we can now look at the engine type, and here are the engine types that came from our systems model, and we can make a choice, and that will then filter our configuration in our bill of materials automatically. And that all fed all the way through from our high-level system design. As well as those productivity benefits and gains that speed up the move from the systems model into PLM and also improve the quality, we know that change will happen over time, and to check the impact of those changes we need to build in traceability. So maybe the requirements change, which changes the system design, which then has a flow down change to parts in our PLM system, or maybe we have new parts that are available, changes to parts based on other inputs, which then we need to check still implement the system design and the original requirements. So let's take a look at traceability in action. So here we're starting with PTCs Windchill with a structured set of 4 parts, and starting out they have no trace links to in any models in Integrity Modeler. Okay, so if we open the new PTC Navigate Manage Traces app, we can see two panes. On the left, we can browse to Integrity Modeler servers, and on those servers we can see the model databases, and inside those model databases we can see the models and their versions. We can also create bookmarks for any of those items so that we can jump to them more quickly. So here's an example again of the same model we were looking at earlier, and we can drill down and find the blocks representing system parts here that we want to link and trace to our PLM system. Here in Windchill we can then select the part, choose the type of trace and apply the trace. That then creates the trace link for us, and if we open the tabs at the bottom of the screen, we'll now see the trace links that have just been created between the model and the PLM system. So let's create a few more trace links so that we can use them in a moment. We can do one-to-many trace links and create them at the same time. Or simple one-to-one links. Now that those links have been created, if we come back to Windchill and look at the Traces tab, we can see the link traces back out to Integrity Modeler, back out to those blocks. So here we have a link to the powertrain block, and here we have a link to the drive shaft block, and here we have the chassis subsystem and the drive shaft. From here we can, if we choose to, remove links, so clear them, and then they're deleted as links. We can also see a lot of information about the system item. So we have a nice icon, the version of that item, more information that's given from Integrity Modeler, the server it's on, its title, the type of thing, and the trace type. And the information view then also lets us jump immediately across to Integrity Modeler's web client, where we can see more detailed information about that block. We could also trace from here to find out the functions it is used for, implements, the requirements that that function implements. We can also see the diagrams that that block's used on and understand a lot more about the system design. From PTC Navigate Manage Traces, we also have more information. So we have details about the parts and also details about the system block, and also other points to link across to both Integrity Modeler Rich Client and the Integrity Modeler Web Client. So straight from the tracing environment we can jump straight into Integrity Modeler, right on the item that we were following. So here we have the chassis subsystem. Again, here we can see more information about the diagrams that that block is used on. Based on those links, we can then open those diagrams and continue modeling as a systems engineer. So as a systems engineer, I may add more information, more properties, more functionality, and as I'm making those changes, Integrity Modeler will log those changes with an electronic signature and a timestamp. This is standard change tracking in Integrity Modeler. But what that's done is made the link suspect, and in here in Windchill we can see the link was suspect, and once we've checked the link is still okay and that those modeler changes haven't had an impact on the trace, we can then remove that suspect flag. There's a kind of to-do list of reviewing the model changes. As well as jumping to the rich client from PTC Navigate Manage Traces, we can also link to the Integrity Modeler web client. Here we're jumping into the chassis subsystem properties, and we can see things like the rich description. And just to close off on this tracing and integration, from the Integrity Modeler interface we can also see which Windchill PDM link parts are linked to each of the blocks, and then automatically jump to Windchill to go and see them and look at their information. So very deep lifecycle integration from the systems model and MBSE to Windchill for PLM. So now let's take a look at systems engineering process governance. As well as the tools and techniques to use during model-based systems engineering, we also need to consider the process of systems engineering and how we govern that process. In PTC's MBSE solution, we provide out-of-the-box documentation for industry standard systems and software engineering processes. We provide these in a tool which give you core processes which you can then enhance with your own best practices based on your real-life projects. We provide updates to those processes over time, and you can then use the tool to configure the process, tune the process in a modular way with editing and authoring. The tool provides automatic process diagramming using a web-based multi-device user interface. You can use it to run projects and gather metrics for improvement of the process in the future. And it also has a very powerful process tailoring wizard to give you truly agile processes based on answering simple questions about your product or your system and generating project workflows for that project. The core process that we provide is the PTC Integrity Process Perspective. It's a model-based systems engineering process based on industry standards like ISO 15288. It has three main parts which match to the things we've already talked about in the presentation. A process for model-based systems engineering, an add-on optional process for asset-based modular design, and an add-on optional process for model-based product line engineering. It consists of approximately 311 techniques with 200 tasks, identifies 22 resources and 50 products. That said, you can then use this as a framework and extend it, configure it to match your own best practices. So it's a starting point. It saves you lots of time researching different model-based systems engineering approaches, but then you can use it as a starting point to carry on and tune and improve and create your own best practices for model-based systems engineering. But at the core, it's our recommendation for using PTC's model-based systems engineering solution. Many customers use both that process and approach along with the whole PTC model-based systems engineering solution. So let's take a look at a few examples. Firstly, Alstom Transport, who build train systems, rail and rolling stock. They use the whole suite of PTC's MBSE solution. They use model-based systems engineering, they're moving into asset-based modular design, and they're already making great use of model-based product line engineering for their product families and variation. They found that our modeling technology significantly improves quality and consistency and reduces effort throughout the whole design lifecycle. Next, we have Chira, who build air and space flying test labs. With PTC Integrity Modeler and PTC's model-based systems engineering solution, they've dramatically improved the quality of the work while reducing the time taken to keep their artifacts consistent throughout the design lifecycle. Another example is PSA Peugeot Citroën, who use the MBSE solution and PTC Integrity Modeler as their tool of choice for their global infotainment system. Integrity Modeler significantly improves the quality of the global infotainment system engineering process at PSA Peugeot Citroën, reducing the project design time and development costs. And then finally, Safran from Snecma, who build jet engines and rocket engines. They had the challenge of not having a model-based systems engineering process or tools. And while they started with some best practices in simple documents, they really wanted an approach to document that more widely and improve it over time. So they used PTC's MBSE solution with the starting point of our MBSE process to enhance that process and deploy it across all their systems engineers. So those are 4 very simple examples of PTC's MBSE solution in action. So just to summarize what we've seen, PTC's MBSE solution can help you dramatically improve the design and validation of complex systems. It responds to the current trends in the market, but also is based on best practices. It helps you with multidiscipline collaboration. The solution runs live on a scalable multi-user database. It integrates with other tools in your tool chain, such as Integrity, Lifecycle Manager, and Windchill. It's standards based for that common language of communication for your systems design. It supports things like SysML and also other standards based around model-based systems engineering and variability modeling. It also provides system level simulation so that you can visually simulate your system's functionality with the model in the loop, and then optionally extend to have other things in the loop such as ThingWorx and the Internet of Things. As well as that simulation, we can then automatically generate artifacts from the system models. We can generate documentation, but also automate the generation of code to C++, Java, etc., and also our own technology, ThingWorx. It also includes new and groundbreaking asset-based modular design for breaking models up into systems of systems and linking them with an asset library. It provides unique and groundbreaking variability modeling with a parallel and orthogonal variability model that you can link to your underlying systems family model to give you the ability to configure products in a visual way and run real trade study analysis on the various options. And it also provides a very agile, incremental, modular and minimal approach to modeling, so you do just enough modeling to get the system designed and get the product delivered. These set of unique features of PTC's MBSE solution make it invaluable to our customers, and I'm sure invaluable to you.